Hello everybody. Welcome to the course of Dalimil Mazáč here. I worked out a little presentation. So Dalimil obtained his PhD at the Perimeter Institute under the supervision of David Gaiotto. You confirm? And he had then two postdoctoral fellowships. The first one at the Simons Center for Geometry and Physics at Stony Brook, and the second one at the Institute for Advanced Studies in Princeton. And then I joined the IPhT in 2023. So Dalimil is a mathematical physicist working broadly on quantum field theory and quantum gravity. I would say that his main topic is conformal field theories, where he's an expert of the conformal Boostrap technique, which is the subject of this course. In his PhD thesis, he introduced the notion of analytical functionals to derive a rigorous bound on some theory, and this concept turned out to be very fruitful and used in other contexts. Well, this is more tentative. It's currently investigating in relations between conformal field theories and spectral properties of hyperbolic varieties and other activities. You confirm?
That's all true.
Okay, good. So please.
All right. Thanks a lot for having me, for the introduction, Ricardo. Very nice. And to all of you for coming on this great Friday morning. Yeah. So the course will be on bootstrap methods in mathematical physics. There will be 5 lectures. Basically from now until the end of November. Most of the lectures are on Fridays at this time, but not all of them. There's going to be one lecture on a Monday, which is not the next Monday, but the Monday afterwards. That was going to be, I think, after lunch. I'm not exactly sure what time, but you can check all of this on the course website. Speaking of the course website, there will also probably be lecture notes, which I'm working on. So they're not there yet, but I'll keep updating some version of lecture notes, covering maybe in a slightly more detail the things that I'll be talking about in this course. All right, so what are bootstrap methods? Well, they are some kind of broad umbrella term for a collection of methods which are useful for making progress in mathematical physics. So how do we usually make progress in mathematical physics? So we are interested in understanding some situation, and typically we have some model for the situation, and we'd like to understand as well as possible. Now, in the ideal scenario, you can solve this model exactly, and then you can basically answer all of the questions that you want by the exact solution of the model. But examples, I mean, most of those examples are the harmonic oscillator, hydrogen atom, or 2D Ising model, Verosov model, things like that. But the issue is that the situation is quite rare, so you usually cannot solve your model exactly. Typically, you can solve your model exactly when the kind of the amount of symmetry more or less corresponds to the amount of unknown of the degrees of freedom. If your model is finite dimensional, you can basically always solve it, like just finite degrees of freedom. But typically you cannot do that. So if you cannot do that, what do you do? So one thing you can do is to approximate it. So you can approximate your infinite dimensional model or situation by some finite dimensional situation. So for example, when you're doing quantum field theory, you can put it on a lattice, and then you make the lattice finite, and then you can do everything on the lattice. But this is not okay. In general, this can be very useful and powerful, but it also has some drawbacks. So one drawback is that it may be computationally very expensive. If you want, eventually you want to remove this truncation, you want to kind of go back to the continuum limit, say, and this may be very hard, especially if your theory is strongly coupled. And it's also hard to control errors in this case. So it's hard to make it rigorous if you want to understand things more rigorously. This is usually not the right way to do it. So the alternative is the bootstrap. somehow the Bootstrap is a useful method which are useful when you want to make things rigorous, and when the system is sort of not integrable, when it's chaotic. And the idea of the Bootstrap is to not make any approximations, really, at least initially, but rather to try to formulate some set of axioms which are supposed to be valid for the actual system that we are trying to study. So the non-perturbative object, like the critical 3D Ising model, the non-perturbative CFD say, but the idea is much more general. So the idea is to formulate some elementary axioms, usually some kind of algebraic axioms, and satisfied by the system. And and extract information from the axioms. So, for example, prove estimates on various quantities, use them to estimate. Use these axioms to rigorously, or as rigorously as you want. Of course, you may not, as physicists, we may not always be interested in the most rigorous result possible, but it can be done in principle. Use them to rigorously estimate quantities. For example, in the context of CFDs, you can put some rather rigorous bounds on CFD data, like the scaling exponents, and structure constants, and remarkably, these bounds are often quite sharp, quite good. So this terminology I borrowed from the conformal Bootstrap, but since the resurgence of the conformal Bootstrap, the method has really spread over theoretical physics. It found many applications, and I'll talk about some of these applications in the course. But also, all these applications came from the Bootstrap. But in fact, it was discovered the same kind of ideas has been resonating all over math and physics. Independently of the Bootstrap, it was discovered independently. For example, in the context of sphere packing, similar ideas also apply, and they actually led to the solution of the sphere packing problem by Wiazowska and collaborators in 8 and 24 dimensions. So this is also something that I'll talk about, including the connections of that to the situation conformal field theory. So the typical situation is that your system is characterized by some infinite set of data described. Like some infinite set of spectral data or some kind of data. For CFD, this would be the scaling exponents and structure constants. And the axiom then leads to some infinitely many constraints. Too many constraints, and these constraints can be equalities or inequalities. And so one important aspect of the program is to understand how to deal with this huge system of constraints and how to extract the information most efficiently from it. Yeah, so quite remarkably, this usually works very well. So by carefully analyzing these constraints, it's often enough to produce very good estimate. And in this course, I'm going to explain this method in various examples and see how it works. But somehow the motivating question, which is not often emphasized, I think, in say previous course on the Bootstrap, is to try to. So I'll try to explain why, in my opinion, these methods are so powerful. So why does the Bootstrap work so well? And but in my opinion, and which I'll try to illustrate, the reason why it works so well has to do with an important theme in mathematics, which is some kind of correspondence between algebra and geometry. Very broadly. So this is going to be quite vague, but I think it's appropriate for the first lecture of the course. So a very important theme in math is a correspondence, roughly speaking, between algebra and geometry. So typically, you're interested in studying some geometrical object, which may be hard. So geometric object may be manifolds or topological spaces, or say algebraic varieties, so solutions of polynomial equations. And the idea is to axiomatize these objects in a different way, essentially using the algebra of functions living on these objects. So that's where algebra comes in. So this is really somehow the starting point of algebraic geometry, where you axiomatize algebraic varieties, which live here, so they are solutions of polynomial equations, in terms of the algebra of polynomial functions living on them, and then you can translate questions about. You can basically find a correspondence between algebraic varieties and commutative rings. So you can understand the theory of varieties using the theory of commutative rings, which is somehow much more robust and clean. But it's much more general. For example, you can study locally compact Hausdorff spaces in terms of their algebra of continuous functions on them, and then there's a correspondence between commutative T-star algebras and locally compact Hausdorff spaces. But it's really a very general theme. And an important aspect of it is that really once you axiomatize it, you not only want to see that these axioms are necessary, so that somehow everything that lives here satisfy the axioms, but it's also sufficient that somehow any solutions of these algebraic axioms, which are satisfied by this algebra of functions, is actually an object, one of these geometric objects. And that I think I would like to argue is the case in conformal bootstrap. So conformal bootstrap is an algebraic characterization of conformal field theories, which is the property that all of the solutions of those axioms actually are physical. They actually live here. Now, in the classical situation in mathematics, this is usually commutative algebra. So on all three examples that I gave, there's some commutative algebra, but it can also be generalized in non-commutative cases, and that's actually the case in conformal field theories, where you have some algebra operators which doesn't commute, so it makes it much more interesting. And something else that should be said about CFT is that unlike in these concrete math cases that I mentioned, for CFTs we don't really understand the right hand side. We know how to formulate these algebraic axioms that come from Bootstrap, and we strongly believe that they describe some beautiful mathematical objects which should live here. But we don't really know how to actually produce these objects in general. Like there are various partial methods. You can work on a lattice. You can take the continuum limit at a critical point, and that's supposed to produce such an object. But it doesn't really have the same flavor as the cases in mathematics, where both sides are more or less complete. Both sides are completely understood. You know how to produce all of the examples. So in the CFT, we don't know how to produce all of the possible examples of the solutions of the full bootstrap. It's how much. It's a more open subject. Okay, yeah, that's I think enough for the broad introduction. Maybe are there any questions about it? General blah blah.
Give some concrete example about geometry for CFT. What does it mean that we don't know the geometry for CFT?
Well, we don't, except for a few cases in 2 dimensions, we don't know how to produce the mathematical object which would solve the bootstrap axioms. In the case of the 3Dism, well, you could say you can put it on a lattice, then you can go to the continuum limit, but it's sort of a convoluted object which has many intermediate steps. So somehow we would like to have maybe, I don't know if it's possible, but in an ideal world, you'd like to have a complete description of of say the 3Dism CFT at the critical point without referring to the lattice, and maybe this is true. Okay. But geometry is supposed to be in quotation marks. It's just like geometry is supposed to mean some concrete thing that satisfies these algebraic axioms. You see how in CFT the situation is very asymmetrical. We understand exactly what is it on the left, what are the axioms, but we don't know how to produce examples.
Maybe can you give an example in mathematical physics where you know both sides?
Yeah, that's what the course will be.
What would you call an answer? You would call an answer like an action, for instance, which you know that.
One relatively decent answer in 2 dimensions is are the mathematical constructions of CFTs. So for example, at Liouville, for Liouville, we understand this, or at least we have one possible answer for this. Maybe it's not good enough because you can really show, you can compute the 3-point functions, and then you can prove that they satisfy the thing on the left. Okay, so yeah, the course will really build on examples of a situation where both sides are more or less well understood, except for the CFT case. And the different lectures will cover different examples. So here's a partial list. Maybe there will be a few more examples in the actual lectures, but this is the plan. So the first example is bootstrapping quantum mechanics. Another example is statistical lattice models. Another nice example, which I think is not as well known in our community, is our systems of ODEs. For example, the Lorentz system of ODEs, which many of these things exhibit chaos, so they're certainly not exactly solvable, but they can be analyzed successfully using these bootstrap methods. So these things kind of are prototypical examples of classical chaos, and you can bound long-term averages of observables using these ideas. It may not be the best place to write, right? Sorry, I didn't realize this whiteboard. Yes. Then at some point, conformal field theory will emerge. Field theory. And okay, I need space for 2 more, but maybe I'll just write here. Hyperbolic manifolds and spectral geometry of hyperbolic manifolds. So how the spectrum is the spectrum of Laplacian instead of filling dimensions. And finally, sphere packing. And it's possible that eventually there will be some slightly different permutation of these schemes, but sphere packing. And okay, so these are various interesting examples where these methods are powerful. But what's also interesting is that actually there are very strong connections between various of these items, in particular strong connections between conformal field theory and hyperbolic geometry and conformal field theory and sphere packing. So in this case, it's not just similar in spirit, but actually the formulas are the same. Okay, that's all for the introduction. Yeah.
Just go back to this algebra geometry thing for a second. I think in D dimensions, we don't really know the full axiom, so we don't think that the local data is enough to fully specify the theory. Do you think that making this correspondence more explicit will rely on understanding that part of the algebra side better?
Yeah. I think so. I think well, I mean, I don't really know much about the future, of course, but I think yes, in higher dimensional conformal field theory, there is also important progress to be made on the left, and it may well be that this will inform what should be the ultimate thing on the right. But still, the algebra is still much better understood at the moment in higher dimensions than the geometry quotation mark. I agree with you.
And in 2D, where it's not really an issue on the left, we still don't understand this, so maybe that's not.
There could maybe be some different algebraic formulation in 2D also, you could imagine. But I think in 2D, of course, we understand much better than in higher D what the ultimate algebraic formulation probably should be, I guess. Any more questions? The Chuck situation is a bit simple. Oh, okay, that's great. Whole box of chunks. Okay, so the first example, actually, example which doesn't appear on the list, so maybe 0th example is 0th example is 1D integration. So which may sound kind of stupid, but I'll show you that it's already quite interesting. Or measure theory. All right, so here, in this case, the geometric objects that are supposed to be described by some axioms, eventually, are measures. Generally, they can be measures on sufficiently topological spaces, but for simplicity, let's just focus on measures on R. So R, real numbers, is a topological space. It has a natural set of measurables. And so what are some examples? So the most important example is the Lebesgue measure, the usual one that we like. Lebesgue measure. How we spell it? Dx is the uniform one. Or when you have some measurable function, some positive measurable function f, then you can multiply the measure by f, which is another measure. That's dx. This is still not a more general thing. The measure, you can have a discrete measure, even just a measure supported at a finite set of points. Some coefficients mu j, say, some positive coefficients mu j, and delta function at xj. And to realize the most general measure that you can write down takes the form. So the d mu is a df is like df, or f is some non-decreasing right continuous function to positive numbers. And what this function means, of course, is that when you integrate the measure between 2 points, integrate the function 1 with respect to the measure, then you just get the difference between the function at the endpoint and the function this way. Okay, so this is the description of the geometric things, which are measures. But now, what are the algebraic axioms satisfied by measures? Well, one thing you can do with measure is to, of course, integrate functions. So when you have some function f, so function from R, say R to C, then you can construct a linear functional which takes your function and integrates it. So let's define phi of f to be the integral. So if we fix some measure mu, arbitrary, and you integrate your function against this measure, and so that this defines a linear function. But we could try to characterize measures as linear functions, but this is not really so it's necessary, but it's not sufficient. So there is something extra that we can deduce about this functional, which is positivity. So what positivity means is that if So whenever we have this linear functional, and if f is a positive function, so it's positive everywhere, then phi of f is a non-negative real number. Okay, now it turns out that this is actually enough to characterize measures. So any measure corresponds to a linear functional on the space of continuous functions, which is positive. So an all positive function is positive. And conversely, whenever you have such a linear function on a space of functions, then there actually is a measure which gives rise to it. This is the simplest example of the kind of algebra. So linear function is like a linear algebraic thing, and this is the simplest example, maybe of this correspondence. So it sounds kind of abstract, but it can be made very concrete and quite useful. You can just use this idea to do integral. So to look at some nice simple examples. Let's restrict to let's make our life a little bit simpler. Make connection to the moment problem, the so-called hamburger moment problem. So we restrict to measures which are such that this functional phi is finite when we act on all polynomials. Okay, so this is for example not true for the Lebesgue measure because you cannot integrate x to the n. You don't get a finite answer. But let's just restrict for simplicity to such measures that the integral of x to the n is always finite. And now we want to impose positivity. So we want to impose positivity on all positive polynomials. You can characterize positive polynomials as polynomials which are absolute value squared of polynomials. So if p of x is a non-negative polynomial with I guess with real coefficients, so suppose it's real, so it has real coefficients, then there is some polynomial q, the complex coefficients maybe, such that p is q and q bar. It's a simple exercise. You really just factor p of x into linear factors, and then you can construct q from p. Okay, so now let's write q using its coefficients. So it's x maybe n, c and x, c and yeah, and this function will be positive for all such q's, which means that so phi of p now becomes a double sum of the n and m from 0 to capital N of c and bar of the action of the function on x and plus. So I just plug in this and I expand, so get something bilinear in the c's. And now this function needs to be positive for all polynomials q, which is the same as the statement that if we define this matrix, or let's define a matrix, a kind of an infinity by infinity matrix whose entries are these are moments of your measure, then the truncation of this matrix, n and m range from 0 to capital N, finite square matrix. So this matrix should be positive semi-definite. This is the statement that this is really like equivalent rephrasing of property. Like, is it positive? So what does positive semi-definite mean? Well, it means literally that. What is the definition of this thing? It means that for all vectors C, CNCM, AMM is non-negative, which is the same as saying, well, this is a symmetric real matrix because the measure is real. It's the same as saying that, so it has sort of real eigenvalues. It's the same thing as saying that the smallest eigenvalue is non-negative. All of it. So this is an interesting nonlinear infinite dimensional space of any set of inequalities which are nonlinear in the in the moments. And so this is a necessary condition, but it's, as I said before, it's also sufficient. So at any time you have a collection of moments, so let's call them, let's just call them phi n for simplicity. So let's define phi n to be the nth moment. So whenever you have a sequence of real numbers, such that if you build this matrix, and if this matrix is positive semi-definite, then there actually is a measure which gives rise to this collection of numbers by integrating against x. And now let's see how to use this idea to compute some concrete integrals. I'm not saying this is the best method to integrate in 1D, but I want to illustrate that in real works. To compute concrete integrals, you need to add a little bit of information, because so far we've axiomatized all of the measures, and if you want to commute a concrete integral, you want to zoom in on a specific measure. So let's say for simplicity we just do the Gaussian measure. Nu is the normalization, well, I guess. The normalization is 1 over square root of phi e to the minus square root over 2 dx. A big measure. Okay, then what can we say about the moment? Well, one thing you can say is that when you integrate a total derivative of any function, if the function vanishes at infinity, then this is 0. So let's compute the total. Let's compute the derivative of x to the n to the minus x squared over 2. Well, this is n times xn minus 1 minus xn plus 1 over 2. And if you integrate this, you find that for this particular measure, this implies that n, so from the first term, n times p n minus 1 minus p n plus 1 is 0. So you get a recurrence relation for the p's. So phi n, so let's solve this, is n minus 1 is phi n minus 2 per side. We know that phi of n is 0 for n odd, and phi0 is 1. This is a parabola, so it's normalized. I'm going to be assuming it's a parabola to measure. So phi0 is 1. Now you can actually use this use this equation to solve for all of the phis. So from this recurrence, by starting with 1, you get that phi n is n minus 1 double factorial. So here I didn't actually use the positivity at all. This was just like a motivating example, but it's a correct answer. This is just a Gaussian integral. So the nth moment has to be the number of contractions of n. That's right. Yeah. So it should be using the Wick's theorem. It should be just the number of possible pair contractions of n objects, which is indeed n minus 1 double factorial. Okay, so this is a little bit boring, but now let's do something more complicated, and let's add positivity. So now instead of the Gaussian measure, let's do something slightly non-Gaussian. Let's say d mu is some normalization times e to the minus, you can put some coupling g minus gx squared minus say, x to the 4th. And actually, let's already do this in Mathematica. It's going to be faster. I don't know if you saw my email from this morning, but I encouraged you to bring your laptops and you can follow some of these computations along using Mathematica, your favorite software. Okay, this should ideally it should appear there.
Me too.
Oh, it just needs to wake up. Maybe I can unplug it and plug it back in. Do you think that's a good idea, Ricardo?
Sorry?
If I unplug.
Yeah, try that. Yeah, I'll try another thing on the same.
In the meantime, if there are any questions. It sounds almost trivial, but I promise that as the course goes on, the complexity will increase.
Ask a premature philosophical question. So you had this beautiful picture. We had an algebra, this geometry of these objects, these axioms, and objects that correspond to solutions of those axioms. And then you included positivity after all of that. So do you think positivity is integrally part of the central framework, or is it just a happenstance?
Well, let's see. I think in all the examples where I know that things work, like where you can actually use these axioms to say something, there will be maybe there are cross-counter examples, but in all examples I'll discuss, positivity plays an important role, and I would include them in the algebraic axioms. Positivity can have many different flavors. For CFTs, maybe you don't have to it doesn't have to be reflection positivity, but some other kind of positivity. In the case of this integration, so actually this is kind of an example, right? In the stupid Gaussian case, we had no positivity and we could still solve the problem just from some algebraic identity. But now, when it's non-Gaussian, so let's see, non-Gaussian, we can still do something. Right. Okay, so we do 1D integration. Big enough?
No, I'm.
Oh, there's a.
Yes. Okay. Not full screen.
Oh, no. Okay. All right, so let's try to do integrals or moments of this measure. So minus g x squared minus x to the 4th. Okay, this is some non-Gaussian integral. And like we said, we have a total derivative. So the total derivative integrates to 0, which is going to give us some recurrence relation. Let's divide by that. So let me just collect the different powers of x. There, in this case, there's 2 of them. Okay, so see that there's some 3-term recurrence relation. This is supposed to be, so the linear function of this is supposed to be 0. So actually, let's shift it so that the highest power is n. And then we can solve for x to the n, for the expectation value of x to the n. So by putting it on the right hand side, we divide by 4. So here we divide by 4, we get 1/2. So we get that the nth moment for coupling G, so G is just a parameter of the measure. The nth moment is the n minus 4th moment, which is from this term, and this becomes the n minus 2th moment. Okay, what else do we know? Let's also input the fact that the moment is 0 whenever n is odd, so the condition. So when odd q of n evaluates to 0 when n is even, and to 1 the false or true, depending on whether n is even or odd. So let's input that, and then we know let's impose that it's normalized, so that the 0th moment is 1. Okay. Now this recurrence is enough to determine all of the moments in terms of the second moment, right? Because it's a two-term recurrence. So, for example, the 4th moment can be recovered from the 0th and 2nd. So let's just parameterize the second moment. So it's going to be our unknown. We are basically trying to solve for the second moment. Let's call it A. And this is it. The trick is memoization, so that we don't have to kind of recursively compute all of the moments. Every time we compute a moment, we tell Mathematica to remember all that has been computed up until now. And to make it a little bit nicer, okay. So now we can just compute some moments. So let's say for coupling U to 1, well, this is just A, just linear polynomial in A. So A is the second moment, and actually all of the moments are now some linear functions. Some linear functions of A. And we like to know what A is. So let's compute this matrix. So this is called the matrix A. It's called the Hankel matrix. Hankel matrix, which is going to depend on the coupling G and also the size. So we can only implement a finite matrix, and it's going to be a table where the rows and the columns go from 0 to n max, and the entry at location mn, at coordinates mn, is just the m plus nth moment. Okay. All right. Yes, so this table, and well, now we'd like to impose that this first let's just look at this matrix. So matrix. So you can see that when the sum of rows and columns is odd, it's 0 because the odd moments vanish, but it's just some matrix whose entries are linear functions of A. And we'd like to impose that it is positive semi-definite for all sizes, at least for some small sizes. So one way you can do this is to compute all the eigenvalues. Actually, pretty fast. We set A to 1. If it's a natural number, let's try to do it analytically. So let's tell Mathematica that this is a real number. Oh, okay, I see. Because A is not a parameter here. We do it like that. You see that here this matrix is not positive semi-definite. So 1. So the second one is definitely not 1. But actually, I realized last night that there is a function in Mathematica which tests positive semi-definite of matrices. So it's just a function. So let's fix the coupling to be 1, and let's look at various sizes. And this is This function, yeah, see, so this function basically takes concrete. It doesn't work with abstract. So let's do it the way I was originally doing. The eigenvalues, then take the minimum of the eigenvalues. Let's actually make it smaller. So now the matrix, I'll do it a little bit more readable. Module, now the coupling is 1, and we can change nmax here, make it a bit more clean. So let's say nmax is 1. And now we can use this nice function reduce. We want the minimum eigenvalue to be positive, to be non-negative. I was expecting that this function is going to give me a lower and an upper bound on A. Does anybody know what I'm doing wrong? So essentially, this function reduce is quite nice because if you give it a bunch of inequalities, it's
Maybe you can use reduce with comma and specify the variable a at the end.
nice. I didn't have to do that yesterday when I was trying, but somehow, well, mathematical behavior is a time-dependent thing. Okay, so for nmax equal to 3, you get some bounds which are quite close to each other. When you increase it, some it really behaves. Okay, let me cheat a little bit and see what I did yesterday. That was matrix set precision. Maybe I set this to be. I think the only thing that I was doing differently is that I was defining it like that. Doesn't work. Here gave me basically for any size of the matrix, it gave me a nice lower and upper bound on A, which ultimately converged to the right answer.
Oh, you were using equals and
Sorry. I think that what it doesn't like is this function minimum. I should just impose that all of the eigenvalues are positive, not the minimum eigenvalue is positive. Or no. Yeah. Okay. So we get again lower and upper bound on A, and you can check that this is probably correct. So actually, in this case, you can do the integral analytically. X squared and e to the see that we got the right answer. Maybe in terms of Bessel functions, and we want to normalize it. So now we take this divided by that, and for g equal to 1, it's this number 0.23396, which is indeed in these bounds. And if you can start asking various questions like how fast does this converge as we increase the size of the matrix. how do you generalize it to other integrals? So one thing that I also tried yesterday, but I don't think I won't spend time doing it now, is to make this a higher degree polynomial. Then what's going to change if you change the degree of the polynomial is that instead of a 2-term recurrence, you're going to have a, let's say, 4 or a higher term recurrence. Already for a polynomial of degree 6, you cannot do this analytically, but this method still converges very fast. So I think this is the end of the motivating example, and after the break, we are going to see how to make this non-abelian and quantum mechanics.
Questions, maybe?
Yeah, questions.
We accept questions also from the online virtual room. We will hear you.
Come back. Before I go to quantum mechanics, let me just show a slightly more complicated example. This time I'm not going to dare to do it in real time, because apparently that didn't go as well as I thought in the first case. But this is the case of a higher degree polynomial in the exponent. So now it's a measure minus x squared minus x to the sixth, where now you cannot do the integrals analytically, unlike this case where we can do it in Bessel functions. So here the current relation is obtained by doing a total derivative of this object, which gives you again a 3-term recurrence relation, but now the shift between the powers is 6. So to jumpstart it, you need 2 even moments. So you need the second moment and the fourth moment. So that's what I'm doing here. Let's actually clear everything. Yeah, so here, still normalize it to a probability measure. So first 0 moment is 1. Other moments are still 0 because it's an even measure. And now we have the second moment and the fourth moment are unknown. We are trying to determine them using this positive semi-definiteness. The nth moment depends on the n minus 4th and n minus 6th moment. That just comes from this. So this thing is supposed to be 0. So I just solve for x to the n. Divided by 6, you get this answer. So let's run it. Now the Hankel matrix is the matrix again of all of the moments where n plus m here, and it depends on a2 and a4. If you look at it now, I suppose we do again a coupling to b1 and max2 and some values for these moments. Okay, this is a relatively simple looking matrix. Again, everything is linear in the moments. You can make it bigger. Okay. And now let's just for simplicity let's define this function is allowed, which is true whenever the matrix is positive semi-definite, and it's false when it's not. So let's define it. Just to see what we are supposed to get. I just run these integrals. So this is the second moment, and this is the fourth moment. Both normalized to be probability measures. Okay. Some answers. So basically, the second moment is 0.2, fourth moment is about 0.1. And when I tried this last night, I got this plot. This is just I can. Okay, I don't want to explain all of these functions probably, but this is basically just the plot of the points which are allowed or the matrix. So that on the horizontal axis is the second moment, on the vertical axis is the fourth moment, and I'm using only 5 by 5 matrix. And this is the allowed region, which is already quite small. Make it even smaller.
How does the error behave as a function of the size of the matrix?
We could maybe try to estimate. I think it's probably exponential. I haven't really played with it, and I don't know the theory too well, but I would guess that it's exponential.
Some good reason why.
Okay, we could try to look at it now online, but given the fact that I want to talk about quantum mechanics, which is maybe more interesting, maybe we can try to do it later. But okay, you can see just increasing the size of the matrix from 5 to 6 by 6, the allowed region shrank quite a bit. Okay, so it's indeed looks like this is indeed a sufficient condition to fully reconstruct the measure. But now we want to go non-abelian quantum mechanics. Now, quantum mechanics is like a non-abelian generalization of measure theory. Non-abelian, and well, what is the, when we had a measure in the abelian case, what is it going to become? A state. So a state is somehow an abelian generalization of a measure. In which sense? Well, suppose you have some algebra of operators, your quantum system. So this is, I'm somehow explaining already the algebraic viewpoint. Then state is a linear functional on A. So it's a functional. So state phi, the thing that was measured before, now it's a state functional from the algebra of operators to say complex numbers, which should satisfy some properties. It should respect the Hermitian conjugation. So when we, maybe I can use the daggers. So when we complex conjugate or Hermitian conjugate an operator, we really here you can be in a framework of C-star algebra, so you don't really have to have a Hilbert. You don't have to talk about a Hilbert space, so you can just take this to be the star operation in your C-star algebra. And this thing should be real. So when you take a star of your operator and apply your state to it, you get complex conjugate. It should be normalized. So when you act on the identity operator, you get 1. And finally, it should be positive. Positive means that whenever you act on an operator which is a product of O star times O, then this is non-negative. Okay, and this is what a state is in this operator algebraic formulation of quantum theory. And why is this a state? Well, in the case when you can describe a state by density matrix, it's basically a density matrix, and this functional is just the trace of your operator times the density matrix. So rho. So suppose you're saying that in a situation where the notion of a density matrix makes sense, like finite dimensional quantum mechanics, or just even infinite dimensional quantum mechanics, but maybe not always in quantum field theory. Does density matrix make sense? But let's assume it makes sense. So what do we know? Well, first trace of rho is 1, because it's just total probability is 1. Rho is Hermitian, and rho is positive semi-definite. So this is the definition of a density matrix. And then this linear functional phi of O corresponding to the density matrix rho, it just the expectation value of O is the measurement in your state. So it's trace rho. And you can check that for such a density matrix, these axioms are true. So this follows from hermiticity of rho. This follows from the fact that trace of rho is 1, and the positivity of phi follows from the fact that the probabilities are positive, that the row is positive symmetric matrix. But if you wish, this is like the now in this connection between algebra and geometry, this is like the geometric formulation a little bit. But here it's kind of tenuous. This is the algebraic formula. So we want to talk about states in terms of as linear functionals on the algebra of operators. This is in fact a complete characterization of densimeters. And every time you have such a linear function on your operators, then there is a densimeters corresponding. Now to go, why does this generalize the previous discussion on measures? Well, to go back to discussion of measures, all that you need to do is to take A to be abelian. Right? So if you have an abelian C-star algebra, this is always this can only be realized as an algebra of functions. So under multiplication, algebra of functions on some nice topological space. And then the states. And then all of the linear functionals on this algebra, which are positive, are precisely measures. So this is my generalization of the previous discussion, where we allow the algebra of operators to be non-abelian. And we are going to use this characterization of states to solve some simple, but not as it was solvable, quantum mechanical systems. So just 1D quantum mechanics, quantum mechanics in the Hilbert space on R. So you have two important operators, x and p, which satisfy the commutational relation. X commit p I, and let's take some Hamiltonian p squared plus d of x. I'm not going to put the 1/2 here because some formulas are going to be nicer without the 1/2. P is I, and so now we'd like to use this kind of bootstrap to understand energy levels for various choices of v of x and expectation values of simple operators like powers of x and powers of p. Now, how do we implement the fact that we are in an energy eigenstate? Okay, so phi, we want phi to represent energy eigenstate. So somehow the rho is just the pure state. Energy eigenstate. So let's call it little e because when I use Mathematica, capital E is the Euler constant, so it's better to use small e for energy. Energy E. Okay, so phi is the expectation value in energy eigenstate. What do we know? Then, well, something that you should know is that when we act with phi on the operator, which is the commutator of the Hamiltonian with any operator O, then this is 0. Phi HO minus phi OH is the same thing, but whether H acts on the left or on the right, it always hits the bra or the cat. So it's e to the e I of O minus p of O. So it's 0. But actually, it's also useful to use this constraint that either phi of HO, so this is true for any O, and this is equal to the energy. Keep using the capital E, small e, phi of O. So these constraints are enough to tell the Bootstrap method that we are in an energy eigenstate, and then the positive semi-definiteness of P in this sense will be enough to solve for this spectrum.
Your role as a function using energy eigenstates, you sum over E or you fix the energy.
I fix the energy. So at the moment, abstractly, I don't know what E is, but I know that when rho corresponds to an energy eigenstate, then this is true. So I'm going to treat E as an unknown, as a variable. One of the outcomes of this positive semi-definiteness are going to be constraints on E, as well as some expectation values of simple operators. Okay. So now we have to make some choices, and we kind of want to again play the similar game as before to derive recurrence relations on expectation on the values of this functional. So basically, there's some basis of simple operators which take this form, right? Any operator can be written as some kind of a generalized linear combination of x to the a, b to the b. So what we'd like to x and a and b are some non-negative integer. So we'd like to impose the positivity for all of these operators. But it will turn out to be enough to just impose it for the case of b equals 0. I don't really understand why this is enough, but it looks like you get unique answers for the energies if you just use x to the a. So we'd like to express in a similar, so somehow p of x to the a is like the eighth moment. We'd like to express p of x to the a in terms of some small finite set of moments. In terms of some, basically in terms of p of xj for some finite set of j's from 0 to. And well, to do this, we will use the fact that we are in an energy eigenstate. So we will use these two conditions. So let's see what they tell us. Let's look at this condition when O is x to the n for that Hamiltonian p squared plus v of x. So what's the commutator? The commutator of the Hamiltonian with x to the n. Well, the second term doesn't matter because v of x commutes with x, so it's the same thing as the commutator of p squared x to the n, which is the same thing as p x to the n plus p x to the n e. Now, as you can do, so from the combination between x and p, you get minus I m p x n minus 1 from here. And from the second term, you get minus I m x n minus 1 p. So now you can simplify this even more. Just commute this p. I think that's what I want to do. I'm going to commute this p all the way to the left. So this term becomes this term up to the commutator. Yeah. So this becomes minus 2in p x to the n minus 1, and the commutator, which gives you n times n minus 1 x to the n minus 2. Okay. And now we know that the phi of this is 0. So this gives us an answer for what is phi minus 1 in terms of x n minus 2. So all of them, that of p x to the n, so I'm just increasing n by 1, is minus I over 2 n now. Okay. N p of x n. So that's one equation that's going to be useful. This doesn't depend on the potential or anything. It doesn't even depend on the fact that we are in an energy eigenstate. Oh, sorry, it cannot. Oh, it's enough if I guess if h commutes with rho. Is it true? And okay, so this will allow us to eliminate single power of p, or the pretty good. But now we want to be able to build the recurrence. So we play the same game, but with the next simplest operator, which is instead of x to the n, it's p times x to the n. And see what kind of constraint we get. So now let's play the same game, but let's take O to be p times x to the n. Now the commutator of h and px to the n will receive contributions both from the p squared and from v of x. Okay, so now let's I could just give the answer. But to the n. I mean the second term is easy because the xn commutes with v of x, so it's basically a commutator of v of x with p, which is I times the first derivative of x times x to the n. Okay, so this is what the second term gives us, and the first term is also not too hard. And if you do all of the steps. Find that the commutator of the operator px to the n with p squared is very similar to what we had before. Squared x n minus 1 and minus 1. Now, so once we impose the fact that what we impose is this, that 0 is that the commutator is 0 for this operator, we get that 0 is from this term, we get something that looks like p squared x n minus 1. Then from this term, we get something like p x n minus 2. And from the potential term, we get phi of v first derivative of x, first derivative of v, x. And now we have enough information to get rid of all of the p's. Here, we can get rid of this p by using the first equation. So we transform p of px to the n to p of x n minus 1. So it only involves x. And here, we can replace p squared using the Hamiltonian. Oh, sorry, there is a phi thing. And p squared we can write as the Hamiltonian minus v of x. So once we put the Hamiltonian here, we can replace h by the energy, and then we just get everything depends on x. So what you get is that 0. So from the Hamiltonian term here, you get probably multiply by -1 somewhere, but I'm just going to, just in case, I'm just going to copy what I wrote here. We could probably do it. You can check whether what I wrote is correct. -2n of the energy. Now the n minus first moment, it is this xn minus 1. Then there is the potential term, which is still 2n of e of v x xn minus 1. Now this term we simplify using this equation. Get some xn minus xn minus 2, so we should get xn minus 3. And we get n minus 1 and minus 2 over 2 v xn minus 3. And finally the last term. Yeah, I think to go from here to this line, in my notes I multiply by -1. Okay. So the first term of v times x to the n. Okay, so now you see that everything just depends on x, and when v is a polynomial potential, this is going to give us some recurrence relation for the moments of. Okay.
You can learn more by taking higher powers of p, or does it somehow always reduce to the same rate by taking?
Good. Well, I think if you want it, sorry, you can always eliminate even parts of p by replacing it with the Hamiltonian. You can always write p squared is h minus v of x, so p to the power of 2n. You can do this as many times as you want. So I don't think you would learn anything more. Okay. And now we want to impose that p of when you define the matrix. Now our matrix is A and M, which is the p of x n plus n, because x is Hermitian, and we want this to be positive sum-identical. The claim is that this equation, together with this equation, leads to a unique solution of the problem, provided we impose this for bigger and bigger matrices. So actually, what I did when I was practicing this yesterday a little bit, I didn't try the simplest case, which is just the harmonic oscillator. So let's try to improvise and see if the harmonic oscillator is going to work. Improvising is usually not a good idea, but I hope that for harmonic oscillator is good. And then we do the anharmonic oscillator. Okay, so so let me just copy this recurrence, -2me.
Can you zoom a bit, if possible?
I'll make it bigger.
Yeah. Thank you.
Is this fine? Yeah. Instead of, I'm just writing this recurrence, but instead of p, I'm just writing the powers of x. That's 2n, p of x, x to the n minus 1. Then x. Thank you. That is important. -2, x and minus 3. and then the first derivative of x to the n, and this should be 0 once we active the functional. Okay, x minus 1 plus 2 b of x minus 1. I think, does this look like what is on the blackboard? Okay. Now for the harmonic oscillator, v is just a quadratic function. So we plug it in as an abstract function. You can do it like that. X is x squared. So this is just the argument. Okay. Then it's a recurrence relation between we just 3 different parts of x, n minus 3, n minus 1, and n plus 1. So let's collect parts of x. And let's solve for this for the highest power, which is x and function. Let's also put by 1. Now let's solve for the highest power of x. So we should multiply this by minus 1 and divide by 2n. Okay. So this the p of n should be this. P n minus 4. P n minus 2. This is some property of the harmonic oscillator. Let's see if it can give us the spectrum of the harmonic oscillator. So what we can do again, actually let me quit the kernel. So we forget all the previous definitions from the first part of the lecture. And now the moment. So first of all, the other moments are still 0 because the symmetric potential. Okay, let's see what this tells us when n is 2. When n is 2, the second moment is determined in terms of the first moment, but by 0th moment in terms of the energy. So first of all, the 0th moment, which is just the expectation of identity, is 1. Let's put this in by hand. So the second moment is this one. So it's just e over 2 because the 0th moment is 1. And the 4th moment is determined in terms of the 0th moment, the second moment. So everything is determined in terms of the energy alone. There's no other unknown in the problem. So let's just implement this recurrence again with the memorization. This, let's call this the moment minus 4, moment and minus 2. Maybe make it a little bit nicer, like that. So now it's no longer linear. So now the different moments are some polynomials in the energy. Again, define the Hankel matrix of size n max. Be the table of the moments. So when we look at the Hankel matrix, following the matrix, lots of zeros, but also lots of non-zero elements. And we'd like to test the positive semi-definiteness, which before didn't work so well, but I guess in this case It should be fine. And let's just test for various values of the energy. I'm going to. This is not necessary. I should like to use these modules because it gives you more control over variables. But let's just do 2 by 2 matrix, and let's just look at this function for various values of the energy. So the energy should be positive. We can start with the energy at 0 and go to that. What do we expect? So this is a harmonic oscillator. So usually a harmonic oscillator has energy levels which are n plus a half. But in this case, remember it's p squared plus x squared. So actually multiple by 2. So it should be 2n plus 1. So there should be all odd integers. Spectrum should be all positive odd integers. And let's test this. So we are going to look at the table whether it's positive semi-definite for various values of energy in increments of 1 over 10. And it's always positive semi-definite. Now it starts to be not always positive semi-definite. Sometimes it's false. So let's actually select only those cases where it is positive semi-definite, where the second entry is true. Okay, it's true still quite most of the time. Actually, let me forget about the true. So let's only take the first. This is the set of energies for which it's positive semi-definite. Maybe if we list plot them, I think. Okay, there's quite many of them, but now we can start increasing. Plus, here we only get 1 and 3. Okay, so these are the first positive odd integers. It's looking pretty good. 5. We can like to convince you that I'm not cheating, it's just increments, so let's slap a smaller increment. I think 99 over 20. Okay, I mean, as a proof of concept, I think it's probably good enough. Okay, you can really see the spectrum starts emerging. So even if I go in increments of 1 over 20, fine, but we know how to solve an harmonic oscillator, but we don't know how to solve an anharmonic oscillator. That's the analytic. So let's solve it using this method. I mean, of course, you can still solve the anharmonic oscillator using some kind of diagonalization, but this method is going to give you some rigorous bounds on the energy levels and expectation values. So it's not completely vacuum. But still, this first lecture it should just be should be thought of as a proof of concept. Let me show you how it works for the anharmonic oscillator. So we still use this. We still use the same recurrence relation. Just copy the whole. Now let's do some more complicated potential. So gx squared plus x to the 4th. It's a quartic polynomial, and the recurrence has now 4 different powers of x. Minus 3 and minus 1 and plus 1 and minus n plus 3. So let's shift it by 3. We want to solve for the highest power of x. So we want to multiply this by minus that. right. Let's clear what used to be the moments. Now I also. So this is the correct equation I want to implement, right? Yep. So the odd moments are still 0 because it's an even potential. Now the 0. The 0th moment is still 1 because it's just the identity. The second moment is unknown because the recurrence relation doesn't determine the second moment because it's a higher degree polynomial. But now all of the moments are also going to depend on the coupling. Remember, I put some coupling G because I want to maybe make the mass positive and negative to see some signs of kind of symmetry breaking, or what happens when you have an inverted square potential. Let's put the G into the game. Now, when we G to the 4, we could already do it using the recurrence, but I think it's a little bit, when we put n equal to 4, then there is this term where the mathematic will try to evaluate x to the -2, so I want to avoid that. So I'm just going to put in the fourth moment by hand from this equation. X squared should be replaced by moment G2. Okay, and now the general nth moment.
Did you call it equals?
Oh yeah, thank you. The nth moment will be this thing. So here is the moment n-6. So n-4. And this is the n-2. Okay. Now, what do the moments look like? Well, let's actually define the Hankel matrix. I think I probably want to define the Hankel matrix at moment G and M. But I also want to define a Hankel matrix for fixed values of the energy and the second moment. Remember now that the moments are functions of they're linear functions in the second moment and some polynomials in the energy. But I only want to define it for some fixed values of these. All right. So now, for example, when we look at the Hankel matrix for coupling equal to 1 of size 10, and okay, let's do some bit for first. Polynomial matrix. Good. And what do we want to do now? Well, I suppose now we want to think about some. We want to test positive semi-definiteness. Let me just get rid of this now. Here we're going to control the coupling, and let's first do positive mass. And here we're going to put the size of the matrix. So let's first make it very, very small, 4. And okay, my Hankel matrix and max, G and max, and it depends on the energy and the second moment. And we are wondering whether this is positive semi-definite for various values of the energy. And because the potential is, if coupling is 1, so energy is positive, we can start at 0. Maybe we can go up to 10. So 1 over 10 again. And now we also need to scan over the second moment, so it's going to be double. It's going to be 2-dimensional array. And again, the moment needs to be positive because x squared is positive. So it starts at 0, and maybe we can go, I don't know, to 5. See what happens. So this, in case this takes too long, I just want to be able to monitor the values. Maybe it's actually slightly better if we evaluate this numerically first. So I'm just going to set the precision. Usually, usually operations are slower with rational numbers or something. Real numbers. Going pretty fast. Oh, it's not. There's a true here. Let's see where it is. Where is it? Oh, I should remember this. Let me again define some function. Is allowed. Is allowed is a point which is allowed. Is allowed Q maybe call it. But I don't want to recompute all of the points all over again, so I'm just defining it to be able to memorize it. To memorize whether it's allowed or not. False. Now I want to plot a two-dimensional array. So I first need to flatten this a little bit. So now this gives me a list of the triplets, which is the two coordinates and whether it's false or truth. And from this list of triplets, I'm gonna select those which are true. So where the third element is true, and I don't want to keep track of the true or false. So let's just do that. These are all the points in the two-dimensional space of energy and the second moment, which are true. And I can now plot them. Interesting. Okay, so it looks like some connected, more or less a connected set, because I'm just doing a discrete exploration. We start somewhere here, so the gas is maybe, this is where the ground state is. And maybe some next excited state is over here. So let's actually go to, let's zoom in close to where you think the ground state is. So let's go between 0 and 2, and 0 and 0.3. And let's do mesh to be slightly smaller, 1/50. Only for 4x4 matrices. So let's do more. I made it a bit too precise. Okay, so we see that the ground state energy should be somewhere close to 1.380. These are the only 3 points, and the working expectation value should be somewhere close to 0.3. Let's see. So one thing, in the rest of the time, I can either check that this is actually true, or I can look at the case of negative mass. Maybe it'd be more fun to look at whether it's actually true. So let's just test it by actually solving this anharmonic oscillator using Hamiltonian truncation. So what's the idea? We set g equal to 1. So the Hamiltonian is p squared plus x squared plus x to the 4. Now we know how to solve this, and we will treat this as a perturbation. The spectrum of this, as we saw before, is all the positive odd integers. And okay, ideally we should do this using ladder operators, but I'm just going to do it in a kind of a stupid way. So let's just build the bases, which are eigenfunctions of the free part, so p squared plus x squared. So that these should be solutions of the Schrödinger equation, which is, so this is the p squared term. This is the x squared term, and this on the right hand side is the energy, which we know should be 2n plus 1 of x, right? Parabolic cylinder D. Well, it's not very nice. It should be the Hermite polynomials. So why is it not Hermite polynomials? This is the solution of the free part with energy 2n plus 1. So let's call it the basis function. Basis. The only problem is it is not normalized. We want to normalize it. We want to normalize it to 1. Unfortunately, I don't remember the normalization. See, what should be the normalization? It looks like there's a square root of pi. And there's powers of 2. Like a factorial. Okay. Now it's normalized. Oh, sorry, but it should be called unnormalized. Oh, I guess I'll just delete it. Normalized. Check it. Okay. That's good. And now we need to compute matrix elements of x to the 4th. So what's the matrix element between the nth state and the mth state? Well, it's the integral of x to the 4 times the product of the two bases. Using ladder operators, this would be more elegant, but actually, I don't want to compute this every time. So let's remember it. Correct. This is going to take too long. You can count a while. Okay. You can do a 10 by 10. That's right. So these are the matrix elements of the potential. And what we want to diagonalize is the full Hamiltonian. So the Hamiltonian is the table where the free part is 2n plus 1 times the Kronecker delta, which is diagonal in this basis. And then this is the potential. This is And we just interested in ground state which is even, so we can work in the even sector. So the comma 2 means that we are jumping by 2. So we are basically only using the even values of n. Max, and max is 2. Matrix. You can compute the eigenvalues. These are the approximate energy levels of our system. For 2 by 2, it's the ground state is 1.4, which is kind of in the right ballpark. So on the horizontal axis, it was supposed to be 1.380, about 1.389. Now we can make the truncation bigger. You can see the ground state is pretty close, 1.39 or 10, 9257. So that's right, but I guess it's just missing the. I could go to higher. We could easily go to higher truncation and max here in the bootstrap to get to the right value. Okay, maybe I can just check this 0.3. That the second moment indeed is 0.3. Okay, so I guess the last. Now we need to compute the eigenvector. I need to find the ground state, compute the expectation on ground state. So let's look at the eigenvector. Eigenvectors are just going to give us. We have on the last one, so that's like element -1. So this is the ground state in the basis of Hermite polynomials. We want to construct the actual function of x. So we want to take the inner product of this vector with our basis, which was 1. So this is the basis normalized of x. So this is the function. And now we want to compute the expectation of x squared in that function. So that's the integral of x squared. Maybe let me just put a line here. X squared. Function squared, where we set y to be equal to x. We integrate from -infinity to infinity, and if the bootstrap was correct, it should be about 0.3.
Is the eigenvector normalized now?
The eigenvector is not normal.
And big coefficients.
Thank you. Now it's normalized, right? Right. It's perfect. Thank you. So next time we'll talk about probably ODs, like ODs like the Lorentz system and long time averages.
Maybe there are some questions.
I mean, in general, when you have the recurrence relation of general form, it's a good idea to introduce these generating functions by viewing this recurrence relation, the guys that are shifted, let's say, f(xn-1) here as the coefficient in some expansion in some additional variable. then you end up converting a recurrence relation to a differential equation for this generating function that depends on one additional variable. Is this a good idea to do in this setup or rephrase things in this setup this way?
Sounds like a good idea to me. I don't know how it depends what your eventual goals are. My goals in this first lecture were just pedagogical. Probably if you want to say something analytic, exactly.
Here you solve for the moments, and from the differential equation point of view, you would solve for the generation function out of those moments. So.
More questions?
Sorry, we created kind of toy models, and now we have this problem that your methods work with productivity constraints. So, in the case of your zeros example, measure theory, I mean, can you evade this productivity constraint and make it work for in more general cases?
So in measure theory, one way you can generalize a measure is a sign measure. So basically a measure which can be both positive and negative. Then you use it positively. And then you can represent any sign measure as a difference of two normal measures. And then I think a lot of the things that can still be done by somehow reducing to the positive case. You're probably asking about non-unitary CFTs, where, okay, I don't know if you can represent the non-unitary CFT as a difference of two units. The existing mathematical theory definitely goes beyond this positivity. And if you're interested in trying to study it a little bit, and maybe present one of the lectures. It wasn't my original plan.
More questions? Okay, if not, thank you again, Jimmy.